Hi, this is Paul Gregg, and I'm going to do a short video on aluminum foil boats. It's not my normal thing. I am actually going to really refer you to a great video that somebody made on the PieStem YouTube channel called Optimal Aluminum Boat. It's really a great treatment of, these... The basic idea is you get some aluminum foil, you put it into some kind of a shape, an aluminum foil of a certain size, put it into a certain shape and fill it with pennies put it in water, fill it with pennies until it sinks. The question is, who can make the best shaped boat? And a lot of times this is just done in middle school or grade school, and there's just some fooling around, just some experimenting to try to do it. But this video at PieStem YouTube channel, Optimal Aluminum Foil Boat, does a really good job of bringing some math into it. Basically, buoyancy is when you float something on the water or in the water. And the basic principle is that the gravity is forcing the object down into the water. And then there's a buoyancy force equal to the volume displaced by the boat, whatever amount of water has been displaced, times the density of water times the gravitational constant. So there's a force acting up, and this is how boats work. And it can get a lot more complicated than this, of course, but that's the basic principle, is that there's a force going down and a force going up, and that force is equal to the volume of water displaced times the density of water. And so that's the basic principle. When you're doing this, I will say that not every penny weighs the same. Turns out before 1962, they were all copper. And then before 1982, they were mostly copper, and they weigh around 3.11 grams. After 1982, they made them mostly out of zinc, and so the density goes down. So you might get a bunch of pennies and you might start weighing them, or looking at the dates at least, and separate them into these two things if you want to be a little more accurate. You can see I couldn't see the dates very well with my eyes. I'm old. And so I just weighed 10 pennies and took the weight in grams, and then 20 pennies. And I must have had some of the older pennies in the second group because it weighed a little bit more. So basically, know how much your pennies weigh. This is... And then you do the experiment, you put them in there, and there's a lot to do here. It depends on how you put them in there, if you balance it, and of course you want to get the most amount of pennies in there as you want. The one I'm familiar with had a 4-inch square piece of heavy aluminum foil, and you make some kind of a boat shape, and the video you'll see. I really encourage you to do this Optimal Aluminum Boat, because she looks at V-bottom boat, a square boat, a spherical boat. And then I said there's several more things we ought to look at. So basically, I'm not going to spend too much time on this. This is her work from the PieStem YouTube channel. Basically, you're looking at the volume of she calls it a canoe, which is just this kind of a shape. You look at the volume of it, the height, and then you just see, the question is which height to length ratio gives you the most buoyancy. And it turns out that's related to the volume. So if you have the equations where you can define everything in terms of H, and then you have to find the equations that let you solve for H in terms of L. And then you can just change H and change the volume, make a chart, make a table of those two things, graph it, and it'll peak at some place. And that's basically, you're kind of getting into the idea of calculus, where you're looking at the slope of a nonlinear line curve, and you're finding the maximum of it and stuff like that. So you find the maximum here, and then you know that when H is equal to 1, this is 4 inches by 4 inches. When H is equal to 1, that's when the maximum volume is. And so that'll be the best boat if you use this shape. Then she goes on to do a square. So you can see that there's the height H and the length L and the volume. And so this is the volume equation. You need to solve for H or L and then plot L versus volume. And you can see from this plot, she uses some other things in the video to do the plotting and stuff. But you can use any spreadsheet program to do the plotting. And then you can kind of either just look at which one is the most volume, and that's to be close to the optimum answer, or just graphically look at it about 2.5. When L is about 2.5, the volume is going to be at its maximum. And then she did spherical as well, I think for just one radius. And these are the equations. You get into some trigonometry. On the square one, she actually did some calculus here, where differential calculus lets you determine the slope of a curve at any point on here. And when that slope is equal to 0, it means it's horizontal, and that's the peak. And that's what she did here. So you can find an exact answer to this problem. Spherical, she also calculated from the weight of the pennies how many pennies the optimum boat should be able to do here. And so there's 26 and 31, and spherical was also 31. In her experiments, these come up with different numbers based on different things. She looked at viscosity and things, and those are great things. If you're going to do a aluminum foil boat loaded with pennies and make a little contest in your classroom, I'd really recommend that video from PyStem YouTube channel. It doesn't have many views for some reason, but it's really a great treatment of this problem. Now I went on and I said, okay, what if the bottom of the boat looked like a cone? And you can get the equation for that, and then do some solving and do the same exact thing. Plot it out, see where the peak is, and you can see where the height and diameter, which will give you the biggest volume for a given 4-inch by 4-inch square piece of aluminum foil. And then I haven't worked this out yet, but and you can do this. There's all kinds of pyramids, with different numbers of sides, and you could work out the mathematics for that and do the same thing, plot it. And then there's a thing called a truncated pyramid, and the more sides this have, the more it looks like a sphere, a partial sphere. And so you can see that's the volume of a truncated pyramid. And you could do the same thing. You could plot it out and see where the peak is, and use some math, not just make a shape of aluminum foil and put pennies in it and see how it does, and then do it again and again and again. Yeah, that's one way to do it, and this is fairly cheap. And in real engineering, to make a big boat, you're spending millions and millions of dollars. You want to have this all worked out mathematically as to which shape is going to give you the optimum, the highest amount of buoyancy. And so that's what engineering is about. It's not just about designing and building and experimenting. Design, build, test, design, build, test. There's an analysis component in there, and that's why engineers go to college. That's the difference between a maker and an engineer. Makers are great. You can design and build and test, and design and build and test, and do really well that way. But if you use some analysis, you don't have to spend the time and money doing so much designing and building and testing. So that's the end of that, and I'll see you later.